All right, we are right on time today with about 5 seconds to go. Let's get into Advent of Code Day 8. Hey y'all, Editor Chris here. A brief aside for today. Part 1 is totally solvable programmatically. You can get out of that hole by just doing what you want to do programmatically. Part 2 today is a very Advent of Code type problem, I will say. You have to have inspected the input because the answer that we use today or have to use today, either of the two possible answers that I've seen people use, both of them rely on the input being formulated in a very special way. So don't worry if you had trouble with part 2. I encourage, if you want to learn about those solutions, go look them up. We're going to talk about one today. One of them is going to be left for you to research if you want to. Just keep that in mind going through. Today is just by definition a hacky solution to part 2. There is no generic solution that you're going to be using. So with that caveat, back to the video. We're still riding a camel. One pouch is labeled maps, which is our input. Maps for how to navigate the desert. One of the documents contains a list of left-to-right instructions, and the rest seem to describe some kind of network of labeled nodes. Ooh, is today the graph day? It seems like you're meant to use the left-right instructions to navigate the network. Perhaps if you have the camel follow the same instructions, you can escape the haunted wasteland. After examining the maps for a bit, 2 nodes stick out, A and Z. A is where we are now. Z is where we have to get to. This format defines each node of the network individually. Left and right, it's notable, is roughly a binary tree. So A, 2 nodes, A, 2 nodes, or A, 2 nodes, B, 2 nodes, C, 2 nodes, etc. Starting with AA, you need to look up the next element based on the next left-right instruction in your input. In this example, start with A, go right. Then L means to choose the left element. Cool. This pretty easy to set up. B-tree map keys of the nodes with values that are the tuples for left, right, and then we just match and we go left or right. Don't need to solve any graph traversal, at least in part 1 yet, as far as I can tell. Of course, you might not find Z right away. If you run out of left, right, just repeat. So this can sit in, I guess, like a vectec or anything that we can rotate through. Basically, we just stick this in an iterator, we make it an infinite repeating iterator, and then we just keep going. Follow the left, right instructions. How many steps are required to reach Z? Okay, so puzzle input, not too bad. Let's grab the test input. We'll just create day 8, the ocho. Looks like everything worked here. We got our input and input.text. Love having that automated. Get our input in here. What's our answer? Our answer is, starting with A, you need to look up the next element. Then L means to choose the left element. By following, you reach Z in 2 steps. And then we have another one. So we could RS test this with this input. I guess we don't need to label these. I don't know why I thought I had to label those. So then we get input here as a string slice, expected. So we can do a string slice here too. Then I feel like I messed up the syntax. Oh, you know what I didn't do? I didn't put the little case things here. Okay, test failure, great, and unimplemented. So we have the first one. Let's get the second one as well. This is going to take 6 steps. Cool. So we've got 2 cases. Both are failing because the thing fails. And then we've got our instruction set. Make sure that while I was copying this, I didn't mess it up. I did mess it up. Let's get one more new line in there. So we've got line of characters, 2 new lines, keys, and values. So we're going to end up with our parser at the top here. Typical nom fashion, same signature as every other day. We're going to have a vec of cars, and I'm going to go with a B-tree map of string slice to string slice, I think. No, string slice to tuple of string slices. Always remember to wrap alt in a tuple. So we've got many1 alternating right and left. This will give us a vec of cars here. Then we should be able to skip the space anyway. We'll do a separated list 1, separated by line ending. We're going to do 2 separated pairs here, I think. An alpha1, a tag of space equals space, and an alpha1. But this alpha1 is going to end up being delimited, open paren, close paren, separated pair, alpha1 again. We'll do a tag this time with a comma space, because I think that's how that works. We need to check the input specifically for this one to see if that space is multiple or not. And then alpha1. And if we save, that all knocks down into a single, really probably too long parser. It helps to read the error messages when they're happening and not as they were 10 changes ago. Oh, this tag is the wrong tag. I think it's from bytes. That's what I get for importing so many things at the same time. And then line ending. Is there an issue with line ending? Separated list 1, line ending, and then separated pairs. Error message needs to be handled. Okay, so this would give us a vec from keys and pairs, and this would be fine, but I would kind of just love to walk away with a B-tree map. Again, I do think we have to allocate this B-tree map here, because if we don't, I think we could loop back in the actual input. If we do it this way, we're not going to start with the white space. So we need to do terminated, separated, pair, and then we'll do an alt here, and alt will either be line ending or end of file. And I have an unclosed delimiter because I didn't end terminated. We'll only ever have this B-tree map or these B-tree map items. And this comes in as key value. So insert key value, return that. Now we should have our B-tree map. And we aren't calling the parser yet, so let's call the parser. So we get our input here, the instructions in the map. The input we aren't really going to look at unless we have trouble. So one thing that could be fun here, actually, instead of just leaving this input, there's this thing called the debug assert. So debug assertions. So we have debug assert equals, and debug assert whatever else. In this case, it's going to be the same as assert equals, but debug asserts are only going to be enabled in non-optimized builds by default. So if we run this in dev mode, we'll get this assertion. So we can always be sure that this input, if we're running in dev mode, after we, write the right phrase here. So we can always be sure that when we're running in dev mode, if our program hits this and we don't have no input left, then we will have an assertion here, it'll fail. So even if our parser succeeds for some reason and doesn't parse everything, now we will know about that immediately. But this will also get compiled out in production. So we've got our instructions on the left here, LLR and A is to BB. A always goes to B, is that true? A always goes to B. I guess that's a no-op, basically. B can go to A or Z. Z can go to Z. So yeah, this is why we can't do that without creating this B-tree map here, because we can go from A to B to A to B to A to B to Z. So with our logic, then, we'll have instructions that iter.repeat, I think. Repeat isn't what we want. What do we actually want? I can't off the top of my head remember. It's going to be called cycle. Right? Repeats an iterator endlessly. Instead of stopping at none, the iterator will start again from the beginning. After iterating, it will start at the beginning again and again and again and again forever. So cycle is what we want here, not repeat. Always useful to go check your functions. If you think that you should be able to do something, go try to take a second. Time box it, obviously spend, 5 minutes looking, maybe not an hour, but always useful to have these functions in your pocket. So instructions iter cycle, that will give us our infinite. And then we can enumerate, which will give us the counts. And then I think we want to find, because this will give us the index and our, I guess, do we call this instruction or direction? I'm thinking instruction because usually it's called instruction in Advent of Code. One thing happening upon this match, so we can absolutely match on the characters here. I think that's totally fine. But doing the match here makes me feel like we've done something that will bite us. So basically, we're matching on characters here, right? And we always know that we can only match on these two characters here, but we store a car, which means we can have any car. So if we do that match later, then we wouldn't be able to, like there's ambiguity in what value is going to be there. So we can remove that ambiguity here, and we can take direction left, or not direction again, right, left and right. And then for each of these, we throw away the value and we create either a left or right, depending. And then this isn't a vec of car, this is a vec of direction. And now when we look, we have left, left, right. So what that means is that when we match down here, what we were just about to do, right? Now we can only ever have left or right. And we don't have this issue of we could have any character here technically, because car is a very big type. It has a lot of different values it could have. So either way, we need to do map.get on the current node. We expect that to always succeed, always exist at a valid node. And then left, well, I guess we could do this outside of that too. So before we match, we have our options. So options.map.get current node. Current node doesn't exist. That's why we have the red squiggle. That's fine. We'll figure that out. Then we expect to always exist at a node. And then this is options.0 for left and options.1 for right. And then if next node, next node is what ZZZ is our, then we're done. Otherwise, we loop around again. So here we can return some index +1, right? So we do have some squiggles here. Expected bool, I guess find map is at least what we want here. We always start off at AAA, and otherwise we set current node to next node. And here we can do let sum step count equals this, else panic. This will never be reached because if we ever have none for everything on an infinite iterator, this will just never ever happen. And then what did we actually need to do with that step count? I guess it's just how many steps. So if we return that, we aren't passing anything because not yet implemented. Do I have a to-do somewhere still? I do. Did I stick that in the parser? Oops. We'd never finished our parser. Okay, so input instructions map. That should be the value from our parser at least. Okay, we're running benchmarks, I can see right here. Very complex type used, consider factoring parse into type definitions. Maybe we'll take care of that later. That's a common one in Bevy apps. Hilariously, we are getting our benchmarks. So we've got 2 tests passing, that's both of our tests. Do we dare actually run this? I guess we don't have any other thing to do. Hopefully this is our step count. Hey, gold star. And now we have to do it in a graph, right? Sandstorm is upon you and you aren't getting any closer to escaping the wasteland. You had the camel follow the instructions, but you've barely left your starting position. It's starting to take significantly more steps to escape. What if the map isn't for people? What if the map is for ghosts? Then I'm calling Ghostbusters and getting out of this desert. Are ghosts even bound by the laws of space-time? Only one way to find out. After examining the maps a little bit longer, your attention is drawn to a curious fact. The number of nodes with names ending in A is equal to the number starting in Z. If you were a ghost, you'd probably just start at every node that ends with A and follow all of the paths at the same time until they all simultaneously end up at nodes that end with Z? What? For example, we have 11A and 22A because they both end with A. As you follow each left-right instruction, you use that instruction to simultaneously navigate away from both nodes you're currently on. Repeat this process until all of the nodes you're currently on end with Z. If only some of the nodes you're on end with Z, they act like any other node and you continue as normal. Okay, so we need to operate on multiple paths at the same time. So we'll need to filter object keys to get out our starting values and our end condition changes. So let's copy into part 2. I don't think we have the same tests. So in this example, new example, we end up entirely on Z nodes after 6 steps. And we'll just get rid of this other case because it doesn't apply anymore. So we'll work on day 8, part 2. Our parser seems to be having trouble because these are now alphanumeric and not just alpha. I think that's true for everything, which is a really easy change for our parser. We do, however, need to bring it into scope, so we did that. Always exist at a valid node is false. That might be because we're just running forever. If we end up at X, that's what happens, it looks like. So if we go 11A and we go to the right, we end up at X, and either way, we end up at X forever. So let's do a quick debug. So a cool thing that Rust Analyzer can do, right? If you don't want to do the thing where you're like, okay, I'm going to select this and wrap it, then you can stick your cursor at the end here, hit dot autocomplete, type dbg, and hit enter, and it will automatically wrap the previous expression for you in that debug. And if I do it inside of this, because that's really where we need it, then same thing happens, and we get AAA. Oh, right, because current node is AAA. We haven't changed our logic yet. AAA doesn't exist. So that's totally valid, actually, as our panic. So our logic needs to change here. We need to map.keys.filter key.ends with A, and I'll collect that to keep that around for a while. We'll call this starting nodes. I guess we don't need this to be starting nodes. This could be current nodes, right? I don't think we know how many nodes we're going to have to actually deal with. So then what we need to do inside of our instructions is for current node and current nodes, we need to do this whole thing. And the setting here is going to happen differently. So maybe we don't do that exactly. So the next node here is going to set based on the index. This is starting to feel more and more like we should be doing a fold here. We got away with the find map earlier. I'm a little concerned about doing mutation like this because I think what we'll end up with is that we're trying to access this as an iterator and also as, so instead of doing it this way, let's do current nodes.iter.map. We'll do current node like this, and then we take that logic, we stick it in here, and because we've stuck it in here, next node is just the return type of each of those maps. And this becomes next nodes. And then we do if next nodes dot all, and they're all equal to something ending in Z, right? So it ends with Z, and then it's some or it's none. So that should work. We've kind of just extended our logic. Next nodes needs to be a vec of string slices, right? Or current nodes. Current nodes doesn't have a type. Sorry, I read the wrong one. Vec of string slices, and next nodes needs an iter before this all, right? Oh, we didn't collect here. Do we need to collect? we do need to collect. We need to collect because here in the none case, we need to reset current nodes to next nodes. And I've typed this as a reference to string, but it's actually a double reference to string up here. Get current node needs to be a reference, right? What is current node? There. Let's look at their type inlays. Current node is a triple reference to a string. I think we actually need to dereference this twice. And then the type of next nodes must be known because we're collecting. So we get a vec of string slices, hopefully. Expected vec of double string slices, found a vec of string slices. We do actually need this to be double references, technically. So we have two options here. I think that the right one is to make sure we dereference up here so that this filter becomes a single reference. So we've got our B tree map here that are string slices, single reference to str. We do .keys. When we filter, because we are iterating over this as references, which is keys, so we get another reference in keys. And then filter is a reference to the item in the iterator. So we get a double reference here, leading to the unique triple reference for key ends with A. So we end up with double references here, but we don't actually need double references. So we can take a reference off by doing key ends with A, then some, dereference key, and that gives us a string slice here, which should give us current nodes. Can't assign because it's not mutable. There we go. And now all of our references match up. References are first class types. And the way that it flows through this map is particularly interesting because we have this B tree map of references. Then we want to reference that. So if we go look at keys over a reference to self, gets an iterator over the keys of the map in sorted order. So we have to be referencing the things in the B tree map. There are solutions to dealing with that to some extent, like .cloned. I chose to not do that just to make it obvious about what was going on. So you can see here .cloned is a method on iterator that creates an iterator which clones all of its elements. So it's useful if you have an iterator over a reference to T and you need an iterator over T. That is exactly what we need, or not exactly what we need, but it's pretty close. So if we've replaced the logic we just wrote with .cloned, then we do get what we expected. That takes one of the references off. So for some reason, our benchmarks up here don't want to die as processes. So I can use nushell, use ps pipe, where the name column is equal to just, and we can see that it died up there. Looks like we have another one running. I am just going to do that one too, even though I don't know what it was running on my computer. Yeah, see, so it just killed that in our terminal again. Now we have none of them running though, so that's cool. So does part 2 pass the tests? Part 2 does pass the tests. Does part 2 pass the actual input? I actually have no idea how long this is going to run for, so that's unfortunate. We could at least bring back, well, even if we do a progress bar, we're not going to know, is the problem. So one thing that I could think of doing performance-wise is basically making this a giant parallelized iterator, right? Because we've got these instructions, we've got this B tree map, we've got our current nodes, and each of these nodes, if we look at our input, how many do we have? We'll do a space or space equals. It looks like we only have 6, so we could parallelize that and run 6 at a time, at least. I would say that we could try to reduce the graph, but that would also involve skipping instructions. I feel like we could have set this up to at least print out a number every, million cases or something. So the thought in my head, this has been running for a little while. I just kind of did let it run just in case it would be, a shorter brute force solution. The thing that I can think of is potentially cycle detection. So if we have, I guess, 2 things, right? One is I don't know when this is going to end. So we could spend some time parallelizing this and brute forcing it, but I have no how long that's going to take either way. And the other one is the actual solution to this as a problem set is probably cycles. See, 11A, 11B, 11B, 11Z, 11Z, 11B. So it looks like it's possible that B to C, C to Z, Z to B, all of these are cycles, it looks like. So we could, by inspecting the input and figuring that out, figure out every opportunity in this cycle that we have the opportunity to land on, and then just repeat those over and over. So we've got we can land on it for node number 2. If it's not 2, then it could be 3. If it's not 3, then it could be 4. And then we loop that around again. But we need to detect that we're cycling back to B here. So we've got this little loop. It looks like the loops always start with the second node, which is interesting. I wonder if that's true for the input. We could also just load this into petcraft and visualize it. Okay, it is worth noting that this ran for 10 minutes. So I kind of just waited for 10 minutes to see if that would run. Well, it ran, but it kept running. So it does take a while. We can do something a little bit silly just to see. So we're iterating many, many, many times. So let's see. I did 10,000, 1, 2, 3, 4, 5. Add a couple of zeros in there. And this is how fast we're doing a million. And this ran for 10 minutes. So if we take usize max and we detect the absolute worst case runtime, it is very long. It will run for a very, very long time in the absolute worst case scenario. So we would at least have to parallelize it. But even then, right, like if we say that we can do this in a sixth of the time, if we're doing one each, that's still very, very, very big. If we get somehow luckier, and this is a U32 size, then it would take an hour. So we could drop that down to 20 minutes to get through, right? 1 hour over 6 is not 20 minutes. That's the wrong math. It's 10 minutes. So we could run this in approximately 10 minutes if we parallelize it, provided that the number that we're supposed to return is not a U64. I feel like the question for me is, even if we do the cycles-based approach, there could be multiple cycles. I'm looking at part 1. This is part 2. So theoretically, we have a cycle for each graph. I don't know that that's true, though. Let me take what I have and save it before we continue. And then we are not going to really use what we have here already, right? Because we need to do cycle detection. Okay, this is a little bit later. I've taken the opportunity to actually review how other people were solving the problem today, because it felt like I was getting stuck doing this cycle detection. And as it turns out, and I'll probably put a note on the front of this video, but as it turns out, due to the way the input is constructed, there are at least 2 ways that you can kind of cheat out on this problem. Solving it generally for finding the cycles and the offsets of those cycles from the beginning of the instruction set is not something that seems to be accomplishable. There are roughly 2 solutions. One is the closest one to what I had here, and that is the LCM that we had earlier, which was very close to actually working, except for the fact that we needed to not be applying it to cycles. It turns out that the first occurrence of the end node, so the first node that ends with Z, is the same length as the cycle. So you can just check for the first node in the instruction set that ends in Z, and that just happens to be the right cycle to match up everything relating to LCM and stuff. So this is a very specific way that the solution was set up. It basically completely ignores a cycle and an offset or any irregular cycles or anything like that. But it is a valid solution that many people were using. So in my code, instead of trying to find the cycle at the location in which it exists actually, at some offset from the beginning of the input, we just look for the Z and we use that full length. The position of that node in the instruction set then is the number that we get back that we pass into LCM, and that gives us our result. So not super happy with the possibility of solutions today. They're not, in my opinion, you can't really program your way out of it. You either have to kind of get a lucky guess or a guess informed by the context of past advent of codes where LCM has been a solution before, or you have to spend time checking the input with base assumptions to make sure that some cut down solution is actually going to work, but it will not work in the general case for all inputs. The other solution that we could have had here is called the Chinese remainder theorem. And I'm not going to cover the Chinese remainder theorem today because I feel like the LCM solution and the Chinese remainder theorem are both cut down versions of the general problem that depend on the input being shaped the way it is. So we're going to stick with the LCM solution today. So with that in mind, we'll get our benchmarks running since we do have the answer already. And remember, part 1 was brute force, so running in 1.5 milliseconds is fine. And then part 2 uses this shortcut. So I'm sure these are slower than some other people's solutions, but I'm totally fine with that for today. I will also say that running all these benchmarks on a Mac when I show them in videos, and the Windows benchmarks always run faster, sometimes significantly faster. Our DAT profile for part 1 is about 50 kilobytes, and for part 2 is quite a bit more. So let's get into the deep dive for part 1, because part 1 is a valid sort of approach here. Let me remove some unused imports. So the base approach here is we get a list of instructions. We have to use those instructions to go from the AAA node to the ZZZ node. You can see that there are actually multiple Z's in this input, which later on led me to believe there could be multiple Z's in the other input, but there were not, which is important. So for part one, we need to parse this instruction set and parse this information into some kind of B tree map, for example, so that we can do a get for these keys and receive these values. And then these instructions, right, left, will either put you here or here, which is going to be tuple indexing for us. So I was a bit messy with the parser today. We got the instructions from the first line using many one and an alternating right or left. So alt allows us to allow either of these to pass, and many one will give us as many of those pass as possible. So this altogether gives us all of the characters on the first line, leaving us needing to kind of chop that white space off. In this case, I chose to use fold many. I don't know that that's the best solution. I was hoping to come back and turn this into an iterator later, so I was comfortable doing fold many and writing this so that it would be a little bit easier to transform into that iterator later, but I don't think that was valuable for the problem today. So we used terminated here and terminating at the line endings. Every line has a separated pair of an alpha. In the second case, in part two, it's going to be alphanumeric, and it's a simple swap of this parser. So it's alpha equals, and then a tuple delimited by parentheses, alpha, comma, space, alpha. So that gives us then a key value pair as a tuple in this fold many. So we initialize a B tree map. We initialize it with keys of string slices and values of the tuples that we're looking for, so the left and the right option, and we just keep inserting those over and over. This setup can actually also work if you do B tree map from. So if you wanted to leave this fold many as many one and get the vec, you can do a B tree map directly from that vec and you'll get the same result here. You'll just do an intermediary collection into a vec. So we return the instructions and that B tree map, giving us those results. We use the debug assert equals here to debug just in case. So if we build our application in debug mode or dev profile, then this assertion will run, ensuring that when we run this program, this input is always going to be an empty string, guaranteeing that we parsed everything. In production, this gets compiled out completely. It doesn't exist. So it's a nice little debug check that won't affect our final runtime. In part one, we start at the node AAA. So we set the current node to AAA, and then we take the iterations and create an infinite cycle of this iterator. So what this will do is instructions is going to be right, left, right, left, right, left, right, left. That will repeat forever. Whenever we get to the end of the iterator, it'll go back to the beginning. In this case, we enumerate with a find map, knowing what I know now, in that we're returning the indices here. This could be dot position, but I'm not going to change it right now. So we get the index and the instruction. We get the current node out of the map, which always has to exist because advent of code input is valid. For each of these options, we match on the instruction that we're supposed to actually use here. And I used an enum for these instructions. So direction left and direction right. I already explained that back when we wrote the code, so I'm not going to do it again. In this case, we do option 0 is left and option 1 is right. This is a tuple that we're indexing into. The next node then is just that string slice from that tuple. So if the next node is ZZZ, then we use that index plus 1. Otherwise, we set this current node, and this might be interesting for people, but you can just have mutable variables like this and be setting that from inside of something like find map. This is okay, it works. Now, if I were going to look for a better function to use there, I would consider the fact that we need to iterate over everything and that we need to keep some state around and think about what lets me do that. The third kind of restriction is that we want to early terminate. At some point, we want to find something. So just something to think about. In this case, find map will return an option, but for us, it will always return some because our infinite iterator, if it ever produces none, it's just going to, keep going forever. This will never stop if it produces none. So this will never happen, so we panic here. And then we return that step count, which is just the index, and we're done. For part 2, it's not that different. In part 2, the problem, though, splits into multiple. So we've got this chunk here and this chunk here. And we don't start at AAA, we start at a node that ends in A. So we start at 11A, and we also start at 22A. So we have multiple paths running at the same time. That's really the key difference here. It's also interesting to note that there is only ever one end for each of these paths. So the input is constructed specially in a way that makes sure that there's only ever one z, and a couple of other things like making sure that the z actually exists at a multiple of the cycle length, which we take advantage of here, as we'll see in a second. So parser, basically the same. We only swapped out alpha1 for alphanumeric 1, so we get all the right node names. Otherwise, very much the same. Our starting node becomes starting nodes. In this case, I chose to map and filter. So starting nodes is going to be a vec of all of the nodes that end with A. So all of our starting nodes. We don't need to collect here. We could just throw that into the iter here, shrug. So we iterate over all of our starting nodes then. And then this map means that we can process each of the individual nodes themselves. So what we end up with here is the current node equals the node. We do our instructions, enumerate, find map again. And this time, the only thing we really change is that we're looking for the next node that ends in Z rather than looking for ZZZ. So once we get that position again, which is basically the same thing we did in part 1, we need to take what is, because of the way the input is constructed, this number is then the cycle number that we can use to put together with the other cycle numbers. So for every map here, we get like a cycle number here. And if we look for the least common multiple of those cycle numbers, that is our answer. So overall, not super excited about this one. I think that part 2 was particularly pathological in the way that it required special input. But if you're here for the puzzles and you're here for doing things like that, then I'm sure you had a great time today. And if you're here for learning programming, maybe consider today either an opportunity to learn about the Chinese remainder theorem, an opportunity to learn about least common multiple if you're unfamiliar with that, or just a problem that it's okay to go check. You know, you don't need to spend 6 hours doing an advent of code problem because a general solution might not be the right approach for the advent of code day. So you really can't program your way out of a problem like this. You have to do things like inspect the input, know about the possible solutions, etc. So I hope you enjoyed the video today. I will catch you in the next one. As always, Discord in the description. Come hang out if you're still doing advent of code. And if you're not, I'll see you in the next video. Later.